Good morning, welcome to Control Systems webinar and seminar, and we are going to see some of the concepts related to the control system. We saw some numerical analysis related to the transforms and complex analysis, which are applied in control systems to solve some polynomials obtained from the transfer functions. Transfer functions are realized as polynomials, and now we are going to see some of the numerical methods associated with some stability criteria. And I had already enunciated the importance of the Roots-Hurwitz stability criterion, then the Nyquist plot, and then the board analysis for the control system polynomials as transfer functions realized. Now we are going to see some of the criterion, how it is derived from a polynomial. We have a polynomial, we don't have the control system function now. We just have a polynomial. From the polynomial, what are we going to derive? What by applying the Routh-Hurwitz criterion. We will have a short look at how a sum or a solution is provided with the root. You can see I have a polynomial, say for example s power n a n s power n plus a n minus 1 s power n minus 1, and this goes on till a naught, right? This is a big polynomial. It is a series. This polynomial can lead to exponential series, logarithmic series. It can even lead to binomial series if the coefficients are manipulated. It can lead to any mathematical series. Now, with the help of series, we can also realize some sine or cosines. Our aim is not that now. We are going to take this polynomial. Whatever we see as functions, we are only getting as polynomials. These polynomials have to be analyzed. Even the transfer functions, they can be a polynomial ratio. They have to be analyzed. Now we have a simple polynomial in series. For example, if I put some coefficients, 1 into s power 3, then 6 into s power 2, then 12 into s plus 8, then this particular polynomial is taken from Routh-Hurwitz criterion. Now I am going to put the polynomial into a type of coefficient extraction, so that this is going to give us some stability conditions. Now what I have here, I have s power 3, and what I have here, I have s square, and what I have here s, then what I have here, I don't have anything. S power 0, I can say I have s power 0. So I have to arrange the polynomial degree. This is called as a degree. The degree has to be arranged from the highest order to the lowest, so that I get all the degrees in the quotients. Then I have to extract the coefficients. The purpose of the Routh-Hurwitz criterion is to realize some information from the coefficients, so that we can arrive at the stability of the entire equation. We have the coefficient here 1. I am writing it as 1 because this is of order 1. So I have the highest order here. I have the highest degree. I am writing it as 1. Then I have the next as the 6. But what is the order pertaining to? It is the next order. That means here the order does not refer to the differential equation. It refers to the polynomial. Differential equation orders are different from the polynomial orders. Now we are applying the polynomial orders only here. We have the 6. 6 I am writing to s squared. Now I have the odd term for s. You can ask whether I can write this 12 here. Can I write the 12 here because it is pertaining to s? No. This particular criterion says that once you have the highest order being arranged, then derive the next value from that determinants or eigenvalues. Either arrive their values from the determinants are eigenvalues. This is what the Routh-Hurwitz criterion says. So we need to know the matrix and determinant method to solve the Routh stability condition criterion. Now I have 1 and 6 written here. Now I have the 12. This is going to be odd term or even term. This is going to be odd term. So I write the odd term next to the 1, that is for the S cube. Then I have the 8. This is going to be even. S power 0. I don't want to write the 8 here. Rather, I want to derive these values. So these values are going to be my roots of Routh-Hurwitz stability. They are not going to be the polynomial roots, but they are going to be the roots of Routh-Hurwitz stability. So I want to extract the roots from the coefficients. I want to write the 8 here, which is going to be even term. So I have arranged the odd term and even term in the form of a matrix. This will contain a 2 cross 2 matrix for me. I can solve this 2 cross 2 matrix and then arrive at some condition criteria so that I get the roots of Routh-Hurwitz stability criterion. Now how do I do the determinant value of this particular 2 cross 2? I have to take the determinant value of this 2 cross 2. Now if I take, I get the 12, 6, 72 and 72 minus 8. What is that 72 minus 8? 64. I have the 64 as determinant value. But what I am going to extract from this, I am going to extract from this a coefficient such that the quotient has to be taken from the immediate next order, that is the 6. So I am dividing this particular determinant value by 6, that equals my root of the Routh-Hurwitz stability. This is the root of the Routh-Hurwitz stability. So what is that I have derived from the root? Where I want to know whether the system is stable or not, but have I taken my sign into condition? If I take the determinant value, I have to take 8, then minus 72, that I have omitted. I have just taken the positive sign of the value. So I want to make sure what does this indicate here in the Routh table. Whether with the sign we can say that it is going to have some real part or imaginary part, or we can say that it is going to have negative real part or positive real part. This is what we want to arrive at. Once we saw that there is no change in the sign, we have all the positive values, 1 plus 6 plus 12 plus 8, we have all the positive values, hence we don't have any problem with this. But this is a change of sign here. When we put a determinant value, there is a change of sign. This means that it has got a negative real part. Negative real part, that means we know that it is a negative real part, but we want to take the magnitude of this one for some time. So what we want to arrive at is 64 by 6 will come closely to around 10, right? So this indicates that this particular extraction root of the Routh-Hurwitz stability criterion, that is 10, derived from this determinant value, it is going to be higher than other coefficients, whatever we have seen. It is going to be higher than other coefficients, that is 1, so 6, then comes 10. 10 is greater than 6 and 1, right? It is going to be higher. So this particular polynomial coefficients are getting on higher. Here it is 1, 6, then 12, and it goes on. Because we have a 10, it is going to be somewhat stable. Then if there is a change of sign in the first column of the Routh table for the system, if there is a change of sign, then it is going to indicate that it will have some real part which is going to be negative or positive depending upon the multiple changes in the sign in the first column of the table. This is the first column of the table, root table constructed. If there are multiple changes in the sign, suppose if it is a 1 minus 6, then if it is a 10 and this is a minus 8, then this will indicate that there are multiple changes in the sign, indicating that this particular polynomial is going to be highly complex in terms of its roots. So system stability depends on two things. One is increasing order of coefficients, increasing values of coefficients, not just order. This is 1, this is 6, and then 12, it goes on. Then next thing is the changes in the sign of the first column of the root table is going to indicate that whether the system is going to be unstable or not. So we can say that this system is stable. Now we have derived this particular determinant value divided by the quotient, which gives us around 10. This is going to be increasing value and says that the system is stable. If it is going to be less, then we can doubt the system. Similarly, we can solve the Routh-Hurwitz condition for any control system, indicating whether it is a stable or not. This is one type of arithmetic associated with the polynomial associated with the control system. It is good to solve in algebraic or arithmetic method. So this we have seen the Routh-Hurwitz stability condition. This does not end the Routh-Hurwitz criterion. Routh-Hurwitz also has got many offsets. Offsets mean the condition has got many offset such that we can say that Routh-Hurwitz criterion has got subsystem, subcriterion, like that. So this is called as an offset. Offset indicates the values that a particular coefficient or a constant term can take, such that it is not going to affect the stability of the entire system. We saw the polynomial s cube 6x square s square and 12s plus 8. We saw the coefficients 12, 8, etc. So what values of the polynomials constants may not affect the entire polynomial is also deciding the stability of the particular system associated to the polynomial or realized by the polynomial. This is called as the offset of the Routh-Hurwitz condition. When we want to analyze the offset, what we want to do is we want to add a constant value to the last term, which is not going to take any of the s term. When we add a constant to the last term, then we can determine how far the offset can undertake a limit. The boundary is being constructed with the loose stability criterion as to say that if the boundary has got a value higher than the constant value, then it is going to be unstable, or if it is going to be lower than the constant value, it is going to be stable. This is how the roots of the Routh stability condition criterion, along with the constants and the coefficients, are going to decide the stability of the system. So first column of the root table is going to see whether there are multiple changes in the signs indicating the real negative parts, and the second columns of the root table are going to contribute to the coefficients derived from the higher orders. And this is very important for the Routh stability criterion. But the offset, as I said, is going to be an addition of a constant to the last term. Suppose we have the 8 here. 8 will be replaced by some constant, some unknown constant, so that we define boundary of the entire polynomial, and we want to see whether this polynomial, if it exceeds the boundary with the coefficients, then whether it is going to be stable or not, depending on the values rising or the first column of the Routh table with maximum changes in its sign. Thank you very much for listening about the root Hurwitz criterion.